Hello. I want to do a quick demo on how we at Delta Computer Systems do pneumatic motion control. You can see in the picture we have two videos going on. One is a screen capture with the RMC tools, and the other is a Logic Cam quick capture of the actual system, which is moving, hopefully in sync. I think there's a small phase delay between the camera and the data that's being captured. The data that's being captured on the graphs here is being captured every half millisecond. You can see there's quite a bit being gathered, quite a bit of information. We have actual and target positions, velocities, the control output, the force, differential force on either side of the piston. We have a pressure sensor on either side of the piston, and then we have the proportional output, the integrator term, the derivative term, the second derivative, and the third derivative terms, all being plotted. Now this is kind of busy, so I'm going to simplify this by turning these lines off. Now, if I stop this, now you can see there are 5 lines, and we have the target position, which is a light blue cyan line, which is underneath here, and that's where we should be. It's generated by the motion generator, target generator. We have the actual position, which comes from the feedback that's coming from this Tempesonic rod, where you can see the magnet just moving back and forth there. There's a magenta and blue line here. The magenta line is the target velocity, and the blue line is the actual velocity, and the green line is the control output to the valve. Now, if the system is perfectly tuned, you should see the red line and the blue line be right on top of the light blue cyan line and the magenta line here. So the red line should be on top of the light blue cyan line, and the blue line should be on top of the magenta line. You can see that it's tuned up pretty well. There's a few little rough spots in the cylinders that we can see. Looks pretty repeatable. You can see the control output try to compensate for the fact that it's hitting these rough spots. But overall, you can see the control is really very stable. And usually when you're controlling a pneumatic system, you have a lot of trouble with it moving smoothly. And here you can see that for the most part it is moving very, very smoothly. So to the hardware is a Delta motion controller. Has 2 analog inputs, one for the pressure on either side, and we use that to calculate the differential force and damping. We have a Tempesonic rod here with the magnet, and then there's a I believe it's either an SMC or a Textron servo valve, pneumatic servo valve, that's off to the side here. It's not in the picture at this moment. The cylinder is a rodless cylinder, and it has sort of a band that the weight is mounted to. So that's what the hardware is. Now, the program that's being executed is right here. It's a pretty simple program. It has, let's see how many steps it has. 5 steps. Okay, that's not too bad. It does a 2 move to an absolute positions to 1/4 of an inch and then to 7 inches. There's a delay in between each one of these moves after it gets to the in position. So you see it doesn't move, then it waits for the in position bit, then it does a delay for a second, then it does another move, then it does a waits for the in position bit, does a delay for a second. This transition rate command is important in that it allows us to seamlessly move from wherever we are on to the sine wave, which is what we're going to execute right here. The sign start command starts, and we have an offset of 3.5, which is approximately in the middle of our travel. It's got an amplitude of 3.5, which means we're going plus or minus 7 inches. We've got a frequency of a half hertz. We're going to run 10 cycles, and this is where we start the position, which is at the peak, and then we can, this is a pointer to a status block, which has other parameters for this command. And when it's done, it goes on to the next step. So basically, this is after the command is done, because it's going to take a while for it to execute 10 steps or 10 cycles. And while it's executing those 10 cycles, we're actually changing the target commands. We're changing the frequency and the amplitude at the same time. And what we're doing is we're increasing the frequency, but as we increase the frequency, we have to decrease the amplitude because the pneumatic system will only move so quickly. So to keep from exceeding our max speed, we have to reduce the amplitude. So we're reducing the amplitude from 3.5 to 0.5, and we're increasing the frequency from half a hertz to 1.5 hertz. And it's doing this every cycle at a rate of, well, basically it'd be increasing at 8 hertz per second. So then we wait for the end position bit. When we're done at the end of the sine wave, it jumps back up to start the new cycle again, which means we go back up to here. And you can see this little red marker shows where we are within the sequence. So if I scroll this up and down, you can see right now it's going faster and faster with the sine wave. Now it's gone back up to the beginning where it's doing the two large moves. So here we can watch this again. See those are the two large moves. Then it does the sine wave starting out slow and speeding up. We're on step 5, it would be down here. And then it goes back up to the top and does the two large moves to either end, and then it goes executes the sine wave again. So now what I want to do is go back to the graphings or the plots. Okay, there's our plot manager, and let's see, we got our graphs. Move that out of the way for a second. I'm going to start this up. Now I want to turn this off again. Okay, now what makes this smooth move possible is our control algorithm. And this is not just a simple PI control or even a simple PID control. We are actually using a model-based control. I'll show you our parameters for that. Earlier we've done auto-tuning, and then we had to kind of tweak it by hand because the pneumatic system is nonlinear, and it's very difficult for an auto-tuning system to get a nonlinear system to tune up perfectly. So we did do some modifications by hand, but at least we get into the ballpark. So here you can see we have the model. These parameters were determined by our auto-tuning. And you see we have a gain of, well, it says 4 positions per second. So this means it would go 4 inches per second for every volt that we output to the valve. You can see that it's not quite the same in each direction. Supposedly that cylinder should be symmetrical, but it's not for some reason. So what we did is we used a separate gain going in the extend direction and another gain for the going in the negative direction. The system has a pretty low natural frequency. You got a hydraulic system or a pneumatic system can be modeled as a mass between 2 springs, and a system like that will have a natural frequency. We have a damping factor. The damping factor is pretty high, actually, which makes it easier to control than what you would have thought. But I think there's a lot of friction in the rodless cylinder, which makes it so that the system has an awful lot of what we call viscous damping. And then we have the model frequency, which is how fast the errors between the model and the actual feedback from the temposonic rod correct. So with this model and the second order tuning, what we get from that is a system where we need to use a second derivative. So you have a second derivative, and we have a velocity feed forward. Remember, there's two velocity feed forwards because the model's got a different feed forward or gain in each direction. We have an acceleration feed forward and even a jerk feed forward. Second order systems need to have a jerk feed forward to track properly. So then there's an output filter that smooths the output just a little bit. We're also able to use the pressure force control. We have more parameters here where I can use do pressure force limiting. If I wish to, I could push on, I can set this up to give me 70 pounds of resistance, for instance. This is being run off of 100-pound air from it's a big air accumulator that we have, and there's a long hose, so I'm not really sure what the pressure is at the system. But in any case, we can limit the force or make it so that a force that will, at 70 pounds, it will start to move. And so we can do force control or force limiting, either one. So go back. Do the plots. So because we have a model, and we're using the derivative gains, but you can see the control output is really really pretty smooth, and that's because we're using the model, and that allows us to crank the derivative gains up quite a bit. And in fact, if we didn't have the derivative gains, the output would probably be going up and down quite a bit, maybe a half a volt, and that would just be too much for the valve. You would hear the valve noise. So second derivative gain is definitely important when you're trying to do pneumatic control. And now let me just kind of go through here and show the graphs. Earlier I made a comment. There's two large moves, one to a half inch and then one to 7 inches, and then we do the sinusoidal move. You can see that the peaks, the amplitudes are decreasing in a nice, smooth and linear way. We can do sweep frequencies, logarithmic, and both linear. And obviously you can see we can change the velocities and the speeds on the fly, or the amplitudes and the velocities on the fly. This feature is used quite a bit when we're doing testing. We do an awful lot of testing systems, and the sweep sine waves, and being able to change the parameters on the fly is very, very handy. And sometimes what they'll do is they'll have a test where they'll run at one frequency at a certain amplitude and another frequency, another amplitude, and that's easily set up in the step table, which is our user programs right here. You just specify how many cycles you wish to execute, like right here, and the amplitude, and then you can go on, change the frequencies, or you can issue another sine start command if you wish. Anyway, that concludes my demonstration, and I hope you found this interesting. Bye.